Right. Okay. So hello again, everybody. So here we just got one of the last slides we got to last week, and we were talking about we can have data or information coming from sensors. Then we need to do some signal conditioning, which we will look at in the analog to digital lecture. Conditioning, and this is the Arduino or the microcontroller, and then we've got an output interface. So we can have different types of inputs. So hopefully you can tell me that, or you can see from the diagram there. So which pins are used as being as inputs on the Arduino? You can either type or speak. Oh, someone's going to speak. Hello? Yeah.
There's the pin like 9.
Yes.
9, 7, 5, 3, and yeah, that's it.
5 and 3. So we have essentially we've got 5 volts, then we've got a resistor, I'll draw the resistor, then we have the connection to the pin, and then we have a switch. Digital pins and analog. The input digital pins, they have the tilde sign that we mentioned last week. It's that they can be pulse width modulated. Okay, so then we have the switch to ground. So if that switch is closed, then the pin is a 1 or a digital high. Which would be 255 digital. If that pin is, sorry, that switch, so if the switch is closed, if the switch is opened, then it would be a digital low. Sorry, anybody spotting this error? So if the switch is closed, then the pin would be at 0 because it would be at earth. So the pin would be low. If the switch is open here, then there would be no connection to earth, so the pin is high. Okay. So we can then use the program inside the microcontroller to read whether the pin is high or low. If the pin is high, it would have a value of 255, and if the pin is low, it would have a value of 0. Okay, so for those of you just joined, so we've started off with this circuit diagram here. we have 3 inputs, 3 switches. So we rearrange the circuit diagram so it starts off at 5 volts. So 5 volts here. We have, in fact, we've got a resistor. Then that resistor is connected to the pin. Then the other side of this is connected to a switch, which is then connected to ground. So here we've got the ground and the 5 volts. So when the switch is open, then the pin is high. When the switch is closed, the pin is connected to ground, so the pin is low. Okay. So that's a simple push button input. So we can have many different digital inputs. Here we have what's known as I2C. Now, I2C is a communication protocol that we're going to be looking into a little bit more in these lectures. So it's a communications protocol. And the good thing about it is, so I would like you to have a look, read around at what I2C is. The good thing about it is it only requires 2 wires. I don't know if you are showing something with your mouse. Right, yeah, okay. No, I'm not showing something. Thanks. You can only see it when you can't see it. No, you can't see it when I'm not writing. Okay, so I'll keep writing. So you've got SCL and SDA. So these are the 2 wires. It's known as 2-wire protocol. This is why it's got the 2 here in the I2C. So it's a 2-wire protocol. So as you can see, the other links are connected to 5 volts, VCC, and the ground. And then we've got the data line. So this data line can either be high or low, because it's showing here as either high or low. So that can be high or low. And the clock, oh, sorry, I should say, does anybody else know what the clock should be? What is the EVE port? The EVE port. It is actually, this one, it's 3 volts 3. Because it's upside down. Yeah. In fact, I read it as 3 EVE port, but it's upside down, so it's 3.3 volts, because the Arduino can either output 5 volts or supply a 5 volts supply or a 3.3 volt supply. But good question. So in this case, this particular board requires 3.3 volts rather than the 5 volts. So we have the clock cycle, which then determines when the clock cycle is low, that's when the bit changes from one bit to the next. And then we can have multiple, like this is either a high or a low. Now, the reason that we're going to use I2C, anybody know anything about I2C? Do you know why we would use it over serial communications, for instance? There is less, well, okay. For serial communication, we've got a lecture on communication. Okay, no idea. Good, that's a good answer too. So less wire, there's less wire because there's only two communication, but with serial communication, you have a TX, which is an RX here, and then a TX transmitter and a receiver here. So you can do one-to-one communication. Whereas with I2C, what we can have is we can have one microcontroller and we can have multiple sub, we call them sub devices. So multiple sub devices using the same I2C bus and connection. So we can have multiple devices. So that is what we're going to realize in our practicals. But more about that in your practicals, because this is just the introduction. Then you've also got serial to parallel interfacing. So for this connection, then we have a slightly more complex PCB on the back here, and we use serial to parallel communication. And you can see we've got 1, 2, 3, 4. How many have we got? 1, 2, 3, 4, 5, 6 wires for comms. Plus the VCC and ground. So essentially what we're doing there is we're sending more information, but in this example, we've got an RGB display where it would be split into pixels. So we could send, for example, the RGB values, or imagine sending the RGB values for every single pixel in every single row and column serially. That would take a long time. So we need to use a different protocol that is faster in order to change that display and update. Does anybody have any ideas of other protocols that we use or cables that we use to do this? In your home or in the lab? Yep, exactly. Well done. So you got VGA cables and HDMI. So we can use the serial to parallel parallel interface to control a simple RGB screen, but we can also use those other more complex cables and protocols to communicate in more complex devices. So here we have our circuit diagram or block diagram for our serial to parallel interface. So we have what's known as a master and a slave. So this one is the master device, or the controller. Does that? Yes, but it would have so it works as a liquid crystal. So we're going to be using you're going to be using. I've got them here in the UK, and you in your lab in France. We have 3-color liquid crystal displays. So yes, these have it will be a liquid crystal display with a special library. So we will learn about, or you will learn about libraries and installing libraries. So But yes, it does. So this is the master or the controller device. And then this is the controlled device. And as I said, we can have more than one. So here we've got the all-important clock. And we have master output, slave input. And master input, slave output. Okay? So master output, slave input is this direction. It's master output. What? It is actually meaning slave. So it's, don't really understand. Okay, the master is the one who is in charge of the clock. And other slave devices can connect. So, for example, imagine we have one Arduino. It doesn't have to be Arduino devices, by the way. I have done this with Raspberry Pis and other Arduino, multiple Arduinos. It can be a personal computer, a different microcontroller. So the idea is that we have one device, which is the master, which is in control of the communication. So here, this has the clock. The master does. So it sends the clock to this device and any other devices that are connected to it. So it says, okay, 1 clock period, next clock period. So in a clock period, in this case, we have two wires. So in this case, this has got 4 wires for serial to parallel. This is generic. So master output. So this is coming out from the master. So if this is the device, so say this is the display. This would be your data from the Arduino to a display. Then if any information was being sent back, master input, slave output. So this is coming from the slave back to the master. And then we have the device select or SS. So in this case, when you go low, then that particular device is allowed to transmit. So we can have device number 1, 2, 3, etc. But we will go into communication in more detail. If you and any more questions about master and slave? I know the terminology upsets some people, and I do try and say controller and control, the thing that's being controlled, but in the protocol it is known as master and slave. Okay, so this is just a quick overview. So then we have analog inputs. So we take a continuous valued input signal from 0 to 5 volts. Yes, the master controls the slave. So if we go back to this example, this is the master, the Arduino is the master, and the slave is essentially the output. device, or it could be, for example, or it could be an input device if it was a touch screen. But for our course, we're going to be using I2C as a communicating to another Arduino, so communicating information to another Arduino, and we're also going to be using it to output information to a 3-color LCD. Now, you don't have to use I2C or serial power. You don't have to use any of these protocols to output to an LCD or one of these outputs. However, you would use a lot more wires and it would be slower. So by using these protocols, we can get faster transmission. So then what we do is we have the next process is we've got an input, which I'm sure you all know the difference between analog and digital. Do you? From what you've done with Cedric. So we've got our, yeah, and do you know about sampling? That we have to take samples at particular times. This is just a random signal. Yeah, okay. So then we would have a number of levels. So we would quantize the signal. So we would say, okay, at this point in time, what digital level is this closest to? So we would give this a value. In an Arduino, we've got between 0 and 1027. So how many bits do you think that represents? Data bits. 10. 10 to the power of 2. Anybody do the calculation? Should have MATLAB running. 1024. So we've got 32. Hang on, let me just do the calculation. Well, this came from, it is 1027. If we say, oh, this comes 11. Three to the 10, yeah. Okay. We have, it says 10 to the 20, 10, no, it says 1027, so it's 1028. And I know that we do it from 255. We step it down to 255. So we're saying 1024. I'm going to double check that. So 255. Seems really odd. Okay, I'm gonna double check that value because this isn't this has come from a book. Or shouldn't it be 2 to the power? Ten to the power of 2 equals 1024. But it should be 2 to the power of something, not 10 to the power of something. Two. Am I doing that? Yeah, we're going to say 2 to the power of 10, 1024, which sounds better. And I'm going to double check my source. I apologize for that. But this is a new. Okay, so then we've mentioned already pulse width modulation. It's defined in terms of its period and its duty cycle. I mentioned it last week. So, it's the number of bits in the analog to digital controller for analog to digital converter on the Arduino. So it's 10 bits. So this is a misprint. It should be 1024 or even 1023 because it starts from 0. Yeah, so that should be 1023. And it's a 10 bit. I wish I hadn't asked the question now. Yeah, so it starts at 0 and it goes to 1023. So it's a 10-bit converter that we have on board. That sounds right. I'm not sure why 1027. I'm going to go and change that on the notes. I'm going to make it green stuff. Okay. So it's a 10 bit. It's definitely a 10 bit analog to digital converter. So then we've got pulse width modulation is defined in terms of its period and its duty cycle, the T on and T period. So the duty cycle is 100 times T on over T. And here we have the duty cycle. And if I click on here, we mentioned pulse width modulation. We explained it last week. So what I've got here is I've got an image of an LED. So we're outputting digital. So we're outputting a 1 and a 0 waveform, but it's showing that when we have the maximum off, the minimum off time, the maximum on time that the LED is at the brightest, we start off with 0, and as it comes higher, then the LED gets brighter. So we know that we then have the hardware and software. So we've got the Arduino integrated development environment, and we can write using the Arduino functions, and we can also use C, but we could use assembly language. Now, for those of you after this course wanting to go on to use assembly language, I can give you some YouTube links, which are excellent. So if we just compare quickly, if we use the Arduino IDE and C++ and the assembly language, so that's assembly, Arduino is easy to develop It's got many libraries. It's very slow. And the accessibility of the processor features are very limited. As opposed to learning C and C++, it's a bit more difficult to learn. It also has many libraries, but again, you're going to have a go at writing your own. The speed of the of it running is much faster, and we can access most of the processor features. So if we know the variable names or the processor names, then we can access them. Now, assembly language, it's a lot more challenging. There are no libraries at all, and it's as fast as possible execution. So we can, if we have a real-time application for our microcontroller, then we would be looking at developing assembly language. And we can also access all of the processor functions and features. Because as I mentioned last week, the Arduino IDE itself was written in C. So it's free software. I don't know, have you all got the software on your machines? I know you. No, yeah. Well, if you haven't, I believe that you have been given an Arduino. There is an online software, Mattis, but that sometimes when you want to do more complex things, it's not as functions and things. It's not, well, it's up to you. You can use the online software if you like, but if you want to download it, I suggest you download it. It is, Tinkercad is very slow for simulation. It's good for trying ideas out, Tinkercad. And as you'll see, a lot of my examples are Tinkercad because of showing you from a distance. And it'll be showing you one particular thing at a time. Talking about Tinkercad, I haven't mentioned it on this slide, but I would suggest getting a Tinkercad link account. I'm going to go to it now. So if we go to Tinkercad, if you've not got a Tinkercad link already, I'm going to do a poll. First of all, do you know what Tinkercad is? I'm just interested to see the ratio. Don't worry if you don't know what it is. I just want to know the ratio. So whilst I'm talking, it's a place where you can create multiple circuits, and I'm going to go to eCAN. One of the deliverables for our project. Okay, you know what it is, but you don't know how to use it. I can see that you said one of the deliverables was the Tinkercad, but was everybody on the module, that module? Okay, so Okay, so with it being a group project, some people may have done those tasks. Yeah, okay. So everybody's going to get to use it this time, and those of you that were good at it before are going to be teaching me how to use it. No, everybody else has to use it. Okay. So I'm guessing some of the things that I'm telling you, those of you that have done this, are going to be a bit of a repeat. Okay. So we've got more. I mean, I've got 40 who haven't responded out of your 100. I've got 58 saying yes and 7 saying no. So I would say the majority of you have used it. Okay, so let's move a bit quicker then. So these are all the different alternatives for microcontrollers, and we need to decide how much power we need, ease of programming, speed of operation, do we need interrupts, how to reconfigure, what power and heat settings we need to take into account of. So where is this system being used? How can we interface it? What's the cost and how versatile it is? Can we communicate with other devices? Is it safe? Can we upgrade? Is the memory size enough? Does it have timer counter functions and do we need them? How is it at handling media? And how long does it take to assemble? Does it comply to the electro EMC? So I know what it is. So does anybody know what it stands for? EMC or EMI? Electromechanical. It's to do with the radiation of a product. So does it comply to the EM? So does it not emit the electromagnetic? Does it comply with the standards? What EMP? Perhaps it's different in a. Is that in? I'm just going to look it up. Electromagnetic compatibility. It's what it stands for. Oh, electromagnetic pulse. No, EMC is the electromagnetic compatibility. So the a component needs to once it's operational, before it can be sold to anyone, it needs to be able to withstand certain conditions. So if it passes the tests for these conditions, then it can be sold to the public. I've known it as EMC, but there's also EMI, which I'm guessing is interference. So electromagnetic compatibility and its size and availability. So for most of you, I'm guessing that this is familiar. So we have the code that goes here. So we have 2 loops. What are the 2 loops that we have? What goes in here? The code, yeah, but what does the code have to contain? What does it look like? It contains 2 loops, 3 different parts. What's the other part then? So we've got this. Yeah, I've not put the, I know I've not put the brackets in. Okay, so, and then we've got the variables and libraries. That we're going to include at the top. So the setup loop, the purpose of the setup loop is to do what? So we set up all the input and output pins. We set up any to, for example, libraries. So the pins, input or output. We set up serial connections. If we're, I know it's a general question, but we set up things. So we set up connections to external components, because your external component could be a motor, it could be anything. What's the role of the serial monitor? Okay, good question. Yeah, variable. I've got variable. We've got variable initialization and libraries here, which is the first part. I'm going to go back to the other question. Second part is the setup loop, and the third part is the code. So the serial monitor, I'll answer that question. The serial monitor is when you are sending information back up to the computer for you to view the variables. So you may be viewing the variables in terms of debugging your program. You may also use the monitor is to view them. You could also use the serial connection to send the data to somewhere else. But we could also be using those other communication protocols that I've mentioned, serial to parallel interface or I2C. Does that answer your question, Elijah? Thank you. Yeah, good. Well, the idea is I tend to use the serial monitor when I'm writing code, and then when I know that it's doing what I want it to do, I may, depending on what we're doing, I may remove the printout to the serial monitor because it's going to slow the program down. Then we have the buttons where we verify our code but not run it. The upload button sends it to the board. Now we need to make sure that the board is connected to the correct port. Otherwise, the computer will send the program to a COM port that the board isn't connected to. This will open a new tab, open a new file, save a new file, and that's where you've got the question for the serial monitor. So if you aren't actually writing anything to the serial monitor, you can open the serial monitor and it'll be blank. But in your program, there is a library, and you can say serial write. We'll look at the actual programs later on, but you'll set up your serial connection in your setup loop, and you will write to your serial monitor in your main loop. Generally, you can write to them in the setup loop. So we've got two essential functions in every single program. It's based on the wiring, and every function has those two subroutines that we've just mentioned, void setup and void loop. And also we have includes and define, and these are the same as in the C language. So if we want to include, we need to include our libraries. We do it in that program, and we do have any defines. So if we want to define, say, I don't know, pi equals 3.154. So the void setup is used to set up the board. It executes all the code that is contained between the curly braces, or the ones that you've put down there, which curly braces. And it does it only once at the beginning. Typically, things happen in the setup are setting up the modes of pins, like I said, starting serial communication or even parallel communication, setup of them anyway, and other things that are generally only need to take place once for most Arduino programs. So here we've got the void setup with the round brackets, then we've got the curly brackets or braces, and then the code in between. So then we have the loop, the void loop. So this is a loop over and over again from the start of the program to the end of the program. All the code between these curly braces in the loop, so between here and here, are repeated. A code appears to run in one big loop, and most of your code will have specific conditions laying in wait which will trigger new actions. So we're in this module. Some of you will already have done the basic code, I'm guessing, and then we will then be doing other things that we've not done later on, which is the communications and interrupts and timers. So imagine we've got a temperature sensor connected to the Arduino. When the temperature gets to a certain temperature, a threshold, then you might want to do something. The looping of the code is constantly checking the fan and waiting to trigger the fan. So even though the code loops over and over, not every piece of code is going to be executed every time. So you are going to be, say, if temp greater than threshold, fan equals on, otherwise fan off. But then when we develop this further, we don't want to check sensors every time around the loop. So we will be using an interrupt to say, has this amount of time elapsed? Check the fan. Has this amount of time elapsed? Check the fan. Has this amount of time elapsed? Not check the fan. Check the sensor. Check the sensor. So only check sensor if a certain time or timer has elapsed. So here we've got the diagram, the program. So do we know what this program does? I know that some of you, this will be a very, very simple program. What is this program doing? Can anybody describe it? Does anybody want to put the hand up or just put the mic on to describe it?
Could it be like to lighten an LED,
Yep.
for
So
instance?
we're saying, okay. So we're sending pin mode to LED, the output pin 3, pin 13 has an automatic LED built in, correct? We could also connect an LED using the circuit, and we are sending a high, so making it 5 volts and then making it 0 volts. And we're doing this as quick as we can. Now, if you look at this on an oscilloscope, how do we find out the frequency? We would look at the high and the low and measure that time. And the frequency is 1 over the time. And this can be measured as 121 kilohertz. Now, obviously, we can't see that with our own eyes, which is why we need to use an oscilloscope. If we do the same program, and I'm going to explain this further I'm going to explain it quickly now. Let's just do the So here, if we have this program is the same program, exactly the same program. So pin 13 is output, and I've done it, left it as pin 13 as output here. I can change this and write it in C, and I'll do this in a later date. I'll show you how to do it. So rather than saying void loop digital write, so just using the while one, so forever, if we set port B or equals, now, does anybody know what OX20 means? It's okay if we don't. I'll give you a clue. X refers to hexadecimal. The hex refers to hexadecimal. So if we have a on here, the programmable calculator. So if we are in hex and we have 20, that is binary this. So we've got binary. Oops. Can't show the two things at once. Hexadecimal. Hex 20 equals 0, 0, 1, 0, and then 1, 2, 3, 4. So as void loop goes on over and over is the while. We could try it. I think, okay, I know why. The while, because void loop does go on and on, if you did it with just the void loop and those two lines, port up, port B, then the frequency wouldn't be as high. By having the while one in, then it doesn't jump out and do the void loop, then the frequency is the highest, is higher because it's not jumping out of this loop here. So the frequency is highest because it's just going round and round the while loop, whereas if it comes out and does the void loop, the frequency reduces and you wouldn't get your 2.66 megahertz. So what I'm just going to explain here is the significance of the 20. So 20 in hex and this is 20 in binary. So this is the 0 position. This is the 1, 2, 3, 4, 5, 6, and 7. So port B is mentioned here. Have I got those diagrams? No, I don't. If you remember my diagram that I had before, I've just got a small representation of it here. Port B, the fifth bit of port B, or the fifth, not bit, yeah, bit. The fifth bit on port B represents pin 13. Now this refers to that diagram that this is an excerpt of the diagram that I showed before, which I would like you to all it's in all your practicals or your handouts. I'm not going to go I could just go to it now. Go to another file with it in. Just going to open another file with it in, so just to show you quickly the lab material. So this diagram that I showed last week, so this is a diagram that you need to keep close at hand. So we mentioned all the different ports. So at the moment, this is where we're going to, this is where we're going to, how we're going to be programming. So you can see that we have, Christoph wanted me to explain about this. we have 3 ports. Oops. We have port B, C, and D. So we've got port B, which is port B there, and port B starts here and there. So what we can do is, by addressing port B, I don't understand why in your C code is just right, because we address port B and the number here is this is port B0, this is port B1, port B2, port B3, port B4, port B5, port B6, and port B7. So if this is a 1, as it is in ours, and these are zeros, this means port B, we can either put in a binary number or a hexadecimal number, and we showed that this was, or we saw that this was hexadecimal 20. So in the code, port B20 only refers to this pin. But the point is, when we're setting up the ports, we can set them up in one go by putting a different number depending on whether we want those pins to be input or output. So, okay, got it, thanks. It will be something that you will do in the lab, and it will make it clearer. I know I keep saying that, so let's go back to this one. So if we OR 20, what we're saying is in port B, so on all of those pins, if you OR something with a 1 here, if port B previously was a 0, then we OR that pin with this 1, then the output is going to be a 1. But because we're ORing it, and all the others 0, 0, 0, and 0, 0, 0, because this is the bit of interest, all the others are going to remain as they were. So they're going to stay as they were, because if they were 1s before, they will stay as 1s. If they were 0s before, they will stay as 0s. Does that make sense? I'm going to maybe do a new slide. So if we have 0, 0, 1, 0, so if we OR this, then whatever's in here, because a 0 with, if that was a, let's just say 1, 0, 0, 1, 0, 1, 1, 1. So if those other pins were already set to these values, then if we OR, the resultant would be 1, because 0 ORed with a 1 gives us 1. 0 ORed with a 0 still gives me 0. 1 ORed with a 0 will give me a 1, and this is our pin of interest. This 0 ORed with this 1 would still give me a 1. This would still be a 0. This would be a 1. This would be a 1. And this would be a 1. Does that make sense? So we're making sure we're not worried at that point in time. We're not doing anything to any of these. Now the next line was to knot it with O hex 20. Then closing in C permits us to call. Yeah, that's the point. That's what I'm trying to tell you or show you, that it's faster because we're not using any functions, but also we're able to change multiple pins at the same time. Yes, exactly. Well done. So in order to switch that pin back off, we OR it to switch it on, and we knot it to switch it off. So knot 20 would be 1 1 0 1 1 1 1 1. Oops. So we knot it. So here we AND it with a knot of 20. So the knot of 20 would be 1 1 0 1 1 1 1. So the knot of that would mean if we're ANDing anything here, anything here, anything here, anything here, anything here, anything here, anything here. The point is in this case, we're only changing pin 13. So because we're ANDing it, whatever was in those two would stay the same. Whatever is in any of the others would stay the same. However, because whatever is in pin 13, because it's the resultant of the AND, will always be back. Pin 13 will always go off. I'm just going to ask a quick question. Just so I can get a feel. I'm going to ask a different example. No, we don't. This is fairly advanced, but I'm just trying to get the level because I'm not sure. Why do you have that? Art for on and for off? Good question. Right. I'm going to go on my whiteboard rather than Okay, so we said that zero, zero, 1, 0, 1, 2, 3, 4. So we have an OR because in our other pins on port B, they could be 1 or 0, couldn't they? So in this program, we only want to change pin we only want to change pin 13. We may want to change another pin. So if we had, for example, and I don't want to, am I confusing things? I'm going to put everything, I'm going to put all of these as ones. Just these can be, these could be ones or zeros. We don't mind in this program. But at the moment, we're saying that pin 13 or port B pin or bit 5 is 0. So in order to turn it on, we're ORing it with this number. So we're ORing it because if it was on already, the resultant would be on. So the OR means, the resultant OR means that for all the other bits in port B, they stay the same. So the resultant of this OR would still be 1. The resultant of this OR is a 1. This is a 1. They're all going to be 1s now. But this is the one that we're interested in. Does that now make sense? You see that? I think that's left. Yes, okay. So if we now want to turn it off, we need to AND it with the NOT of hex 20. So the NOT of hex 20 would be 1, 1, 0, all the ones. We've got the same data again. So this is where we're left with. So if we have 1, 1, 1, 1, 1, 1, 1, 1, so the AND of that, these are still going to be 1s. This is definitely going to go back down to low. These are all going to be 1s still. So regardless whether this bit here is a 0 or a 1, the result is after this AND of the NOT is always going to be 0. And here, regardless of what it was previously, like this 0 here could have been a 0 or it could have been a 1. Now that is always, after that OR is always going to be resultant in a 1. So in the same vein, just to see if you do understand it, can you tell me the number? And I'm just going to look at my other PowerPoint. This one. What would be the program to, I'm going to write it down. Program. Can I do this with an answer? No, I can't. How you choose the number you compare hex to. Okay, which is why I was going to give you another example. don't understand how you choose the number you compare the hex to. Okay, so from this diagram here, we've decided that we want to turn a particular pin on and off. And in our case, it's pin 13. So we look at this diagram, and in IDE, it says pin 13 is connected to port B, pin 5. So port B, pin 5 in binary is and that equals 20 in hex. So if I would like to turn on and off, so my question to you now is, I would like to turn on and off pins 5 and 6. And 6, what would the hex number be? Frederick, do you understand how I chose the number in hex now? Forty, 6. Ah, but we just want one number. I want to do it with one line of code. So I want one number. And I haven't worked it out myself. I shall. I should imagine it's higher. Let me see. 1, 2, 3, 4. 1. So we said 6, 7, 6 with 1, 1, 0. Ah, okay, Maxine. Remember we start the first bit as bit 0. Okay, so that's bit 0. So that's bit 0. So, and 7 is at the top, so it would be the last 2 bits. So we have in 1, 1. So what do we have then in hex? I haven't seen the right answer yet. Oh, X, Esteban? No, because this one is B0. It would be 1, 1, 0, 0, 0, 0, 0. So the answer in hex is C0. Oh, what's happened there? Oh, I know. Okay, and now, yeah, C0. Just asking the question. Yep, C0. Yes, that's it. I understand the hex, but you compare it to another binary value. That is the same value. Frederick, I'm using the binary, okay, so I'm using the binary value to show you in terms of the port numbers on 5, 6, and 7. Oh, well done. This is the 6 and 7. Okay, well, we've done an extra. That's the 6 and 7. For 5 and 6, it would actually be, yeah. So for 5 and 6, so that's the 6 and 7. And 7. That's the danger of making things up in the middle of a lecture. So 5 and 6, say is 0, 1, 1, 0, 0, 0, 0, 0. So for ports 5 and 6, it would be 060. Apologies. And by the way, for C2, do we use lowercase c or uppercase c? I would use lowercase. Interesting. I would use lowercase. But for the if you are not sure whether to, by the way, you could use OB and put the binary numbers in as well. So I've got Frederick. I don't understand you understand the hex, but you can compare it to another binary value to get the binary number and the hex number are I may have confused things a little bit. The binary and the hex are the same number. So I definitely confuse things there by saying swapping from one screen to another and changing my numbers around. So I said pins 5 and 6. It depends which pins you choose the binary number by choosing which pin you want to turn on and off. Now let's just go back. This one. So in our case, I'm going to use pins 5 and 6 now. Pins 5 and 6. So we know that pins 5 and 6 are 1, 2, 3, 4, 5, 6, 7, 8 is this bit and this bit. So for pins 5 and 6, I know that some of you understand, but some of you don't understand. For those of you that don't understand, but if we're comparing pins 5 and 6, if we set these two values on port B, not pins 5 and 6, so it's port B, bits 5 and 6. So we would set this one and this one as 0, as 1s, and the rest as 0s. So then we would get O hex 60. And then we would put that in there in the program. To find out what pin that equates 2. In fact, there's a reason that, yeah, that I use. Yeah, so port B, I shouldn't have made these numbers up, I should have prepared them. Port B, pin 5, as we said, was pin 13, and port B, pin 6, doesn't actually refer to an actual pin. So this is an example for that I made up for in terms of to check whether you understood. I didn't check that that's got a port. If we had port D, pin 5 and 6, then that is pins 5 and 6 on the Arduino. So first of all, if we're working it backwards, the first thing that we would need to do is I'll do it for a random port, a random pin. So let's say we want to control pin 2 on the Arduino. So we would look in the IDE which pin it is. It's pin 2. Then it's port D, and it's the second, or the third, because it starts off at 0, third bit. So in our program, we would say, instead of port B, we would say port D. And we would OR it with, and I could OR it with OB for binary, and then I could say it is 5, so 1, 2, 3, 3, 4, binary, 5th one for this one. Beautiful. So port D, or equals binary, and it's the second one, so it is the third bit, so it'd be 0, 0, 1, and we could leave it as that, or I could put in the leading zeros, or I could convert that to hex, and then port D and not 0 binary. So that's showing the example with a different port, so it's a pin 2. Is that clearer? I've got you will have a chance to try these out. Yes, but what is hex? The hex is, the reason that we use hex is because it's to make it easier for us. but we can tell the Arduino will take the hex or the binary as input. So the zeros on the left, no, you don't have to type the zeros on the left. That's just for my explanation to you to show that it is the port D has that number of inputs. So no, we can type 0 binary to tell it it's binary and just type 100. Or we can do O hex and convert it to hex. I can't convert it on the top. The hex. Yeah, the hex is just to shorten it so that a human can read it better. It means exactly the same thing to the computer, to the microcontroller. Yeah, well, it'd be 0B, not 0B, not OB for binary. Yeah. And I do have an example. How do you find the hex? You can calculate it. Okay, today I'm just using the calculator, but we can actually calculate hex by doing 2 to the 0, 2 to the 1, 2 to the 2. You've got a link, yeah, thank you. 2 to the 3. So we've got, and it's 4 in hex because it's 2 to the power of 2. That would obviously be in binary, and then you could convert it into hexadecimal afterwards. And I do have a video somewhere of me doing this for my students, which I can add if you wish. But you won't be doing it in exam conditions, so you'll be able to do it with a link. So what I'm basically saying is, hopefully, if you don't understand it now, by the time we have a go at doing it in the lab, you will understand it. We can turn ports on and off. And by the way, this is for the students that, well, we want you to be able to do this by the end. So I wasn't actually intending on going that deep today, but it's a bit difficult when I'm not. I get the idea that you've used Arduino before, that some of you have had a go at programming. I'm trying to work out what level you're at. Like I say, it was meant to be just a quick explanation of what it is, and then we'll go into more depth later. But I feel like I'm going into more depth earlier. So the main thing is you can see that the frequency that this LED, this is where we started, can switch on and off at 121 kilohertz. Whereas if we use this, we can not only increase the frequency by a huge amount, so 2.66 megahertz. Now you can see that is a vast improvement. But as we discussed earlier, then the ports that are being switched on and off, or the outputs that are being switched, can be done simultaneously. I shall also show you later that we can do shift to the left and shift to the right, but this is the easiest way, using the or and the number, whether that be hex, whether that be decimal, or whether that be binary. It's just that I use the binary is easiest for us to see and to see where the number's coming from in terms of the port bit, the bit on the port. So we OR it with a number, and the 1 needs to be where the port of interest that we want on, and then we AND it with the NOT of that number to switch that port off. If we have multiple 1s in that number, we will be switching multiple digital input outputs on and off. That's the main gist of what I'm trying to say. And we can do that at a much higher frequency than using digital write. So imagine if you had to digital write 13, digital write, I don't know, 9, 8, 7, all after another, then the time that it takes to go around the entire loop of that program, the frequency that it could turn that particular, basically the big frequency would be reduced even further. So that's the main point I'm trying to make. So these are my links to, or this is my link to Tinkercad to show the exact same program. And I know you're all fans of Tinkercad. So this, most of my links are public, so that you can copy them. And you can run this in your own time. So I've given you the PDF with the link, should be active. So if you want to play about, which I will encourage, by changing the LED to a different port, a different pin, and then trying out which, is it going to switch on and off, or we can obviously have multiple LEDs. So if I just start my simulation here, I can see that I've got 100 microseconds on the scale on this oscilloscope, and my frequency is 1, 2, 3 of those wide. So 3 times, I need my other calculator. Can't find MATLAB. One over, I use MATLAB as a calculator just to show. So it's 1, 2, in fact, yeah, it's 3 squares, isn't it? 1, 2, 3 squares, 1 over 3 times 100 times 10 to the minus 100 times 10 to the minus 6. That gives us 3.34. Now this one, I'm going to give a rough calculation. We have just over 1 square and it's 10 microseconds. So it's just over 1 square and it is 10 microseconds. Can't see my answer. So here we've got the first one, we've got 3.34 times 10 to the minus 4, and the second one we've got 0.106. So the code for each of these is this one. I don't know if I know you've done Tinkercad before, but to see the code, then I have Arduino 1, and then Arduino 2, which is my same code here. So that is the calculations for, or those are the calculations for the frequency. What is this? This is 100 microseconds, and this is, yeah. So this is 3 times 100 times 10 to the minus 6. So this frequency is much higher. Obviously, you can see that it's much higher on the right-hand side. It's not going to give us real-time actual frequencies as measured on an oscilloscope, but it's giving us an idea. If we set up the pin mode in C, in the setup function, it could be even faster. Yes, it can. It does look like a problem in the calculations. I'm just going to bring the calculations back. Yeah. Thank you. This is why I have you watching as well. So it's 10 to the power. I was looking. If I go back to the first one, 10 to the power of minus 6. That's better. And here we have that sounds better, doesn't it? So here we've got 3.3. I mean, I was looking at it, but when you're trying to lecture and look at multiple screens at the same time. So yeah, we've got 100 kilohertz. So we've got times 10 to the 5. So if we take, 100 kilohertz and 3.33 megahertz. What is the C code for pin mode? I don't know off the top of my head. I'm going to give it to you because I wasn't planning on going this deep. Where are we? 1050. I can give you an example. I'm just going to find it. Material. We found it in I can send you an example. I'll send you an example on the announcements with the different, for those of you that are interested. I wasn't expected to go into this depth today. I was expected just to talk about different ways of programming. I will send you an example for the pin mode. It's because there's more than one line, and it's to do with the data direction register. And like I say, I wasn't expecting to talk about the code in that much detail. And I haven't introduced the data direction register as yet. Okay, I shall. I don't think I can find it from my Tinkercad link. I've got that many. Which one? But I've got some links. Yeah, it's not one line, it's multiple lines. It's not difficult once I give you the code, but it's not. It's essentially setting some other registers up to say whether it's the data, it is the data direction register for a particular port. So you say data direction register for port B that we're using, and then set zeros and ones, and a 0 is a input. Again, it's remembering which way is which. I think a 1's an output, which is the same as the, yeah, I don't want to give you the wrong information. I will just share you the right link. Okay, so there's lots of reference libraries, and essentially that's where we are. So let's discard. Things take a lot longer. I'm going to actually, what time are we? It's 7 minutes. I'm going to try and find that thing now for you, since since this is where we are. So I'll just do a quick. The thing is, I have too many Tinkercads, and next week I'm going to open lots of Tinkercads before the lecture. I'm just going to search for the right one. Right, so as you can see, I have lots of Tinkercad links. And I think it's the interrupt one. We're not doing interrupts yet, but I'm just going to open that one. Probably taking its time because this one's, oh no, it's not finished. You see the code is here. And again, that will need a bit more explanation. So if you want to have a look at this code, that's what I'm going to do, is I'm going to put it in the comments in this first code. If I just put that in there, and then that'll give you a little bit of work to do. For those, by the way, this is for those that you are interested. I will explain this later, but this is essentially based on what we've done today, and I don't know how large you can see my screen. By the way, I don't know if you know, but Blackboard does have a zoom function, so you are able to zoom into an area of my diagram. So if you can see, you've got, I've just, well, you can't see because I've zoomed in on my screen, but I've zoomed into this area of the code of the diagram, so you can see the code. So this is the data direction register for port B. So port B, and then rather than OX, it's a binary, we just say capital B. And I was asked a question about hexadecimals before. and I think I have, no, I don't have any hexadecimals in that one. However, I'll probably have some hexadecimals on some others. These are what you're going to be doing later on, by the way. You can see I've already have 2 copies of some files. Oh, I need to find the right example. I shall share with you some other examples, or I shall put the code in here. Like I say, I planned on giving you a talk on basic programming in Arduino today. We went off and we've done that extra program, which is extremely important. I will be going through, or I would like you to have a look at this PowerPoint for next week. Some of it may be simple for you because if you've done Arduino before, this is how to use Arduinos. I've got lots of examples there that we can go through. And I've also got lots of other programs. So we'll be going through lots of programming next week. We've gone through the basics of ports this week. I shall probably create a different Tinkercad and see how you get on with ports. If you don't understand totally ports, hopefully you will by the lab session, and you will be doing more inputs and outputs. So hopefully I've not confused you too much today, and we've gained a start off as to what port program is and why it's so important. And it's essentially the moving on from the basic Arduino level up to the more experienced Arduino level. But I will be going through some basic Arduino programs. Now, I'm just going to ask, because I know that there's some of you here, if I put some videos on, last year I created some videos. So what I did is I asked the students to watch these videos, and then I gave them a quiz, a quiz style lecture rather than a lecture, where I asked questions to determine how much they understood. So if I can you watch some? So basically, I'll upload some videos, and if you feel like you need extra, I'm going to upload the videos of this class, but I made some videos especially for Arduino programming, so that if you are one of the ones that isn't so experienced in Arduino programming, then you can watch those videos. So will you what? And then So I'm basically asking if you will watch my Arduino videos. So I made them when I knew that I wasn't coming. Okay, where do I upload the videos? I haven't uploaded a video yet, but they're going to be in, not that window. Sorry, I've already got this. In your Moodle. This one. I've created a folder. So I've created a folder for lecture videos. So at the moment it's empty. So the lecture notes are here. The lab notes will be there. And the lecture videos will appear in this folder. So I've got those. Then code. Okay. So I've got the videos already recorded because I recorded them for last year's classes. It's just that when we're at a distance, it's difficult for me to go at the same speed, get the feedback as if we're in the class. So if we have done a little bit, if you've done a little bit of watching the video, that might be helpful. Okay. Right, it's 3 minutes past 11. 12. Correct myself. So thank you all for your time, and I hope I didn't confuse you too much, and I hope I've taught you something about ports. And if you do have any questions, I can be contacted either on your chat or email. Bye bye. Thank you.